SwayamPrabha.
So in the last class, we have seen a F-vector approximation algorithm for set cover, and we also seen the approximation preserving reduction from vertex cover, so set cover. So that proof we did not cover in the last class, so let's continue that. So today's topic is a two-factor approximation algorithm. For vertex cover. For that, we reduced from vertex cover to set cover, and that's a polynomial time approximation preserving reduction. This is P set cover. So what is the reduction? So let G equal to V comma E comma K be any instance of vertex cover consider the following instance U, S and K of set cover. What is the instance? U is the set of edges. For every edge, I have an element in the universe, and S is for every vertex, the neighborhood of that vertex. Where NV is the set of edges incident on V. We claim that the two instances are equivalent. Okay, how do you show that? So let the vertex cover instance is a ES instance. Let W subset of V be a vertex cover of G. We claim that let's call this set X equal to neighborhood of V, where V varies in W, is a set cover for U. Prove by contradiction. So suppose not. Suppose X does not cover an element E in U, then clearly W does not cover the edge E, which contradicts our assumption that W is a vertex covered for G. Okay, for the other direction, it's exactly similar, but it is important to do it. For equivalence, it's a if and only if statement. One instance is true if and only if the other instance is true. For the other direction, let X equal to NV V. Here also we have cardinality W is less than equal to K. Then we have cardinality X is also less than equal to K. That's what a ES instance of vertex cover means. So V in W be a set cover of U with cardinality X is less than equal to K. Then W equal to V in V such that NV belongs to X is a vertex covered for G. And again, if it is not a vertex covered, then some edge is missed, some edge is not covered by W, but then that edge is also, that the corresponding element is also not covered by X. So, and now we observe, so this proves the equivalence. Now, the two-factor algorithm for vertex covered. So, input is some this graph G equal to V comma E, and we need to compute the smallest vertex cover. Also there could be weight, so it could be weighted. So W maps from V to real number. The goal is to compute a vertex cover of smallest sum of its vertices. Okay, so step 1, let u equal to, or not let, construct an instance u equal to e in e and script is equal to n of v in v. Construct an instance this of set covered. Define the cost of each set. C of S, C of NV, each set is looks like NV. C of NV is W of V for all V in V. Second step, use approximation algorithm use polynomial time approximation algorithm to compute a set covered, let's call it NW, NV, V in W, to compute a set covered of minimum cost then simply output those set of vertices where NV, let's call this set cover X, NV belongs to X. Output this as the vertex cover. So from equivalence we have seen that this is a, so from equivalence, from the reduction, it follows that the algorithm indeed outputs a vertex cover. Okay, now here if we use okay, claim if we use an f factor where f is the frequency of an element, of any element at maximum frequency of any element, if we use an f factor approximation algorithm for computing minimum cost set covered, then the above algorithm has an approximation factor of 2. That's the claim. Proof. Okay, so what is the value of if? First we observe that in the constructed instance of set covered, each element of the universe belongs to exactly two sets from the collection. That is, if E equal to say U comma V is an edge in G, then E belongs to SU and SV only. Hence, the maximum frequency of any element in the set covered instance is 2. Now, because the approximation factor is f of our set covered approximation algorithm, hence we have a solution of the set covered instance hence we have a solution of the set covered instance whose cost is at most 2 times the cost of optimal set covered. But we have observed that, however, the cost of optimal set cover is the same as the cost of the optimal vertex cover. Hence, our algorithm outputs a vertex cover whose cost is at most twice the cost of optimal vertex cover. Okay. Hence, the approximation factor of our algorithm is 2. Hence, the approximation factor of our algorithm is 2. So, next what we will show is another direct rounding approach, also very simple direct rounding approach using LP rounding for two-factor approximation algorithm for vertex cover. This is also simple, but here we are reducing it to set cover. So, next is a direct, and there we will see some more extra structure of the fractional solution of vertex cover. So, direct two-factor approximation algorithm for vertex cover. For that, let me use this as an excuse to introduce couple of notions. So, let consider any arbitrary LP consider any linear program. How does it look like? Minimize in the standard form, minimize summation Ci xi I equal to 1 to n subject to some linear constraints. So, what are the linear constraints? If you recall, it can be written as a x is less than equal to b. Okay, how? This is basically in the matrix notation where A is this matrix A11 to A1n to AM1 to AMN. This and x and b are column vector. So x equal to x1 to xn and b equal to b1 to bn, and this less than equal to means component wise it should be less, each component it should be less. Okay, and of course we have the constraints that x is greater than equal to 0. So some notations, solution is any x in Rn such that is greater than equal to 0, because it satisfies, it needs to satisfy these constraints, and x is less than equal to b. That is called a solution. The second one is called polytope, or it's called a vertex. Or vertex, it has couple of names, vertex or extreme point solution. A solution x in solution x of LP is called an extreme point solution if x cannot be written as a convex combination of two other solutions, if there does not exist solutions y and z in Rn and lambda in between 0 and 1 such that x equal to lambda times y plus 1 minus lambda times z. That means it cannot be written in such a solution. And there is another concept called polytope. So for a linear program, the set of solutions, the set x in such that x is a solution to the linear program is called the polytope of the linear program. So in the next class, we will see some interesting properties of the polytope of vertex cover LP, and using that we will design a two-factor approximation algorithm for vertex cover. Okay, thank you.